As you've probably read, my name is Fabian. I basically am a consultant working in the area of Linux, virtualization, high availability, networking, and I do work for a Canadian nonprofit called Linux Professional Institute. You might have heard about us. We are those with those tests, and if you pass those tests, you get a certificate that we believe that you're good in what you're doing. And yeah, we have a booth here, we have some exams here, and luckily I came to submit this talk. When we want to talk about containers, it's important for me to know what's your background. So I think the best thing to start the day is about the Buzzword Bingo. You probably know everybody these days is talking about Docker, Kubernetes, Istio, microservices. So who of you read about those terms or have heard it? All of you. Who of you try to play around with it, like in a lab of your VMs? And too many run it for real business, like stuff that, okay, 1, 2. And who of you thinks that you really understand what's going on underneath all this stuff? That's good for me. Like if there are 1,000 hands up now, that would be bad. So today we'd like to talk a bit about those technologies and what they actually mean. And I don't want to read those tips out loud because they are no real tips. Those are basically things that I heard people saying. And all of these things basically mean those persons haven't really understood what all this container stuff is about. And in like 40 minutes, you'll all know better. So our objective for today is to talk a bit about application containers, what's special about them, why some of the probably traditional best practices that you might know from administering individual, like real servers don't apply to containers, and we'll take a special view what this kind of containerization means for your applications. So, for example, an application running in a Docker container might find itself in a different environment than an application running in a regular VM. So, as the first part, let's talk about application containers. In order to develop an idea what those applications containers are about, it's probably best to first spend a word on virtualization. That's something that you all know, right? Having a VM, installing an operating system there, having a couple of VMs running on the same host system. So that's something a lot of people know. And that's also something that a lot of people think containers are 100% similar to. So I think we all know why we're doing virtualization, right? We have big servers. We want to segment them into individual parts, to have individual software, to have individual areas where administrators can work with the software without interfering with each other. That's pretty known and pretty well understood. And today, we often have a setup where we have one virtual machine per application that we're running. So instead of having this one big Linux server that hosts web and mailboxes and everything, today we have a couple of VMs, one serving one purpose, and we're able to handle those VMs individually. When we do this with traditional virtualization, like VMware, KVM, all this stuff, then there are basically 4 resources that this virtualization tries to somehow abstract. And that's usually the CPU, it's the RAM, it's a network interface, or more than one, and it's block storage. So that's what the hypervisor is trying to provide for every VM. And then a VM is installing a regular operating system that just feels like running on a real computer. It started, it takes a couple of times to spin up, it has a lot of system services, and yeah, it basically pretends to be in an own environment, although this environment is a virtual machine. The reason why we're doing this is not necessarily a self-purpose. So we're not trying to have, for example, a virtual CPU or virtual RAM or virtual hard disk for the sake of it, but we have it in order to create an isolated environment in which an application can run. But what makes up such an environment? Is it really having like a block storage of some kind? Not really. If we take the perspective of a process running in our Linux system, then this environment of this process is comprised of several other parts. So it's not so much about having a real CPU. It's more about having processes that run. It's about having individual user accounts. It's about working with files. It's not about working with the individual blocks on a hard disk. It's about being able to open a file. And it's not about having a network interface and setting individual bits on the network card. It's more about being able to open a socket and talk IP to someone. So that's a different layer of abstraction, and basically most what we're doing with virtualization is trying to create such an environment by having a virtual machine with an operating system in there. But what if we were able to create such an environment with individual processes, individual files, individual network communication without the pain of running a full VM. If we still have those individual resources and if we're able to isolate them and limit them, then we would basically have all we need in order to isolate processes. And luckily, the Linux kernel provides a couple of systems that allow us to do that. We have namespaces, for example. Namespaces allow us to limit what a process can see in a system. So, for example, there's a process namespace, and processes within this namespace can see other processes in this one namespace, but not the processes of the other namespaces next to it. We have similar namespaces for networking. We have some for mounts. We have some for networking. And that allows us to limit what we see in a system. We have control groups. Those control groups limit what a process can do in terms of on what CPUs is it allowed to run, how much memory may it consume, how much I/O traffic may it create. So that allows us to limit what a process can do. There are capabilities. Capabilities allow us for a specific process to say, what is this process allowed to do? For example, may it alter the configuration of a network interface, even if it's root. So if we have a process running as root, and we remove the capability, for example, to create a device, or to alter network configuration, then this process can't do that anymore, even though it's still running at root. We also have mandatory access control, AppArmor, and SE Linux that allow us to limit what a process can do in a system. And when we combine all those technologies, then we have all we need to create isolated environments within one Linux system. And these things, C groups, namespaces, capabilities, mandatory access control, those are the building blocks used, for example, by LXC, but also by libcontainer, the backend part of Docker, to create isolated environments. So if you try to build a picture of that, we basically have individual processes, and all of them are fenced in a namespace, in a C group. They might have limited capabilities. They might be subject to mandatory access control. And if we do that right, then we are able to create processes that don't see each other and that are not able to interfere with each other. So if you take those two processes up there, then you basically see there's a line in between, meaning that they are subject to those limitations and they don't see and they can't interfere with each other. And that's the basic process of having those containers. They both run in the same Linux system. There is only one kernel, and the kernel makes sure that these fences are enforced. When we think about those containers, we get two different flavors of them. And one of them is the older traditional one that some of you might know. Sometimes they are called system containers. Sometimes they are called VPS, like virtual private servers. They try to put everything that, from an administrator's perspective, make up a system into one of those containers. So instead of having this one process in here, you would have some kind of init system that then creates an SSH daemon that starts a web server, for example. You're able to log into that, for example, via SSHD, and then you're within your tiny namespace, within your tiny C group, and you're able to do stuff in there. For example, LXC is an example for that, OpenVZ. Some of you might Virtuoso, that's a product used by a lot of hosting companies. If you get those like $2 VPS things, they're using this kind of stuff in order to put that parts of the system that make up a server from your perspective into such a container. Usually, the file system of such a container is pretty comprehensive. It has a whole distribution with a lot of services. And when the container starts, it runs a couple of services, including mail server, web server, a cron, a syslog, whatever you want to have in there. And usually, those servers exist for a longer time. You create them once, and then you apply updates to it. You store data in it. When something breaks, you try to fix it by logging in and doing classic administration work. When we talk about application containers, like Docker, for example, then most of these things don't apply anymore. The purpose of such a container is to run exactly one application and to do it exactly one time. So usually we have no init system in there. There's nothing like systemd or like supervisord or anything trying to manage processes within this container, because the container basically only has one process. So we have one container that runs a web server. And the first and the only thing this container runs when it started is a web server. There are no surrounding tasks in this container anymore. At the same time, these containers are disposable, meaning that we just throw them away when we don't need them anymore. If we want to update them, we create a new container with a new version and we throw away the older containers, meaning they can disappear at any time. And that's pretty different if you try to compare it to something like this VPF thing, where you have persistent memory for a longer time compared to an application container that can be thrown away at any time when there's an update. If you think about having, for example, a cron daemon running in the background, or the ability to have an MTA running, or the ability to log into SSH, compared to something where you only have a web server and that's it, then it's obvious that this is not really comparable anymore. I'd like to go into a few of those Docker details a little further with you to first get a real understanding what such a container is, and then we talk about orchestration, and then we talk about what it means for an application. Those Docker containers are always created by an image. That's, again, like pretty obvious. When you have one of those VPF things, you log in and you do yum update and yum install this and that. But if you don't have the ability to, for example, have an SSHD server running in your container, it's not so easy anymore to log in and do administration stuff. So you're trying to create an image that's ready to run. That includes everything your container needs. So you can just take this image, run it, and then you have this one process in your container running. Usually those images contain, of course, the application you want to run, all its dependencies, like libraries, like additional programs that it needs in the background. But usually they are really stripped down to only what you need. So for example, a VI editor is not really needed to run a web server. So a lot of these images won't include it. Some of them even lack less, some of them don't even have some package management, and they're really just like a binary. It's required libraries and a few supporting tools, and that's it. So you get images with only a few megabytes or a few 10 or 100 megabytes of size, which is super small compared to having like a 5 gigabyte default installation of everything that CentOS or SUSE might include if you add a lot of those additional groups to it. Those images are distributed. There's something called a Docker Hub, and this Docker Hub contains a series of images which are ready to use. So if you do, for example, Docker run HTTPD, you'll get an Apache web server running in a Docker container, and that image is downloaded from the Docker Hub. It's possible for everybody to create an account there, to upload images there, which by default are public, but there's a huge library of stuff that's already packed up, ready to run in a container. Of course, you can create own images, and that's basically what you're doing when you're developing applications that are supposed to run in the container. Then you have your own application, and you somehow need a container that, when it started, immediately runs your application. So what you're doing is, usually you take an existing image, and you extend it by your application so that it's ready to run, and then you repackage it as a new image. You're doing that by so-called Docker files, and that's something you probably have seen when you somehow working with some open source projects. Usually on the highest level, there's a file called Dockerfile, and this is a super small example for it. What it basically does, we see in the first row, it takes a CentOS container. So it takes whatever is prepared as that's CentOS, it installs the web server, it copies stuff into the web server. That could be, for example, our application. It sets an environment variable, and the CMD line says, when the container is started, we don't want to have a shell in there, but we want to run the web server. And it's possible to create an image based on this file, and when you do that, you have one image, and when you start it, it immediately runs the web server, and it serves the content that was copied into that directory. So with those Docker files, it's possible to take an existing image, apply changes to it, make it ready for this one purpose that you want to do with the container, and then repackage it as a new image. When you have an image, you can just spawn off containers, and you can use the same image for multiple containers. So it's possible to say, I have my one image, and I'd like to get 20 containers out of it. And all of these containers are ready to run, and they don't have any runtime configuration, which is different. For example, if you say, I have my CentOS image, I start 20 VMs, and then I have Ansible or Puppet configuring all of them. That takes a bit of time. In that case, the image is completed and ready to run. The containers themselves have the image underneath them, but each container gets a small, thin layer in between what the processes see from the perspective of the container and the underlying image. And there's some kind of copy on write functionality. So these intermediate layers are super small until the container tries to modify files in there. Whenever a file is modified, it's copied from the image into this intermediate layer, and read requests are immediately terminated in this intermediate layer, meaning that if the container doesn't write anything to the image, there's almost no overhead. So we don't get a real copy of the whole image. We have only one image and a couple of containers looking to it, with this exception that changes to this image can be stored in this small layer in there. The disadvantage of this is that this, like in-between layer, is specific to a container, and as we've already learned, containers are disposable, so they can appear any time. Meaning, if we have a web server, for example, and this web server writes session information, right? Stores all those PHP session files somewhere, and then we get an update for the application. What we're doing is, we create a new image with the updated version of PHP or our application. We run a new container, which then gets a new intermediate layer, and we throw away the old one. Meaning that we'll lose the sessions, we'll probably lose log files, and we better have not stored any user-uploaded content in this image, because that would be lost as well at that point in time. So data persistency is a very important topic when we talk about containers. The container itself usually is discarded when it's deleted. And when you're using some kind of orchestration tools like Docker Compose, Docker Swarm, Kubernetes, that can happen quite often. So don't expect these containers to run for weeks or for a significant amount of time. Meaning, if you want to store data persistently, it must be in a safe place. And these safe places can either be external services, for example, a database or an object store, or it can be a volume. A volume is like, basically you can think of it like a mount. So we have a device or directory, and you're mounting it into one specific path within the container. For example, if you have a database container, it certainly makes sense to have varlib MySQL on a volume, because otherwise, when you throw away the container, you would lose your databases. So these volumes exist outside of the container. They are mounted into a container on a specific path, and those volumes can be used by more than one container at a time. And that's interesting, because it gives you some kind of shared storage. And as we've learned, each container only has one specific purpose and only runs this one specific task. And most applications need more than one program. So when you think about, for example, your web server who writes a log file, and you certainly want to keep track of what's going on there. So you want to, for example, put it into your Elk stack. So you want a file beat running, observing this log file and pushing all those changes to your central Elasticsearch as an example. In that case, it would make sense to have two containers, one per task. One for the web server, one for the file beat. And you could use the volume as a common path where the web server stores the log file, and where, for example, Firebit is observing the log file and is able to do something with the log data. So you have two containers, each running one process, each serving one task, but you have the volume in the middle that serves as as some kind of exchange point. Likewise, you could, for example, have session data being stored there, and then have a couple of servers all using this session data by looking to the volume. So volumes are a very important part when you think about storing data, and you're not able to put it into another place. So if you take a look to the big cloud providers, for example, you usually get your container runtime, but next to it, you can have a database as a service, or you can have an object store as a service, and that's where you're supposed to keep your persistent data. When we think about those images and that we want them to be ready to run, or like sometimes it's called immutable in the sense of we create them once and then we can run them as often as we want, then configuration becomes some kind of problem, because we want to have the containers ready to run, and we don't want to have any configuration tasks going on when the container is started. So in the ideal world, our application running in the container doesn't require any configuration within the container. So in the best case, for example, everything that we need to parameterize our application would be in environment variables that we can set when we start the container. Or, as like a second solution, it's possible to have one configuration file on a volume and then use the very same container and just connect it to different volumes depending on what kind of configuration we provide to the container. And that's really handy when you think about having, for example, development and staging and testing systems. So I always want to look up who made this quote, and I always forget to do it. There's a famous quote saying, everybody has a testing system. And some people have the privilege of having a dedicated production system as well. And when you think about what can go wrong after testing something and then moving it to the production environment, which always is a little different compared to where you tested it, then being able to use the very same container image for development, for testing, for production, can reduce a lot of potential error sources. Because this container, this image, contains everything you need for your application. It has the libraries, it has all the commands, and there's no difference anymore depending on where you're running this image. So if you're able to decouple configuration from the actual image, you get one generic image that you can use in as many cases as you want. And usually, the best way is to do configuration using environment variables, which you can just set when you create the container. It's possible to put them on files. And of course, it's possible to have some implicit stuff. Saying, for example, whenever your web server starts, or when your web application starts, it tries to connect to the database server using the hostname DB. And then you deploy the web server, the container, in a way that DB always refers to the correct database server. To the production one in production, to the testing one in testing, to the local one running on the developer's machine when you're in development. But the container is always the same. It always tries to connect DB. And DB points to different places depending on where the server is run. So when we think about networking, first of all of these containers get a network interface. It's pre-configured with an IP address, and the container cannot change that. So it's an interface that's created once, before the container is started, is then moved into the networking namespace of the container, and then the container is started with this interface in there. Meaning that the container has no influence on, for example, its IP configuration. Docker takes care of that. But there is an ability for the containers to communicate with other containers and with the outside world. In Docker, it's also possible to have user-defined networks. So it's possible to say, for example, I want one network for application A, and I want another network for application B. Or I want one network for my test installation, and I want another network for my production installation. If you try to somehow put it into a picture, we see, again, two containers, each of them having their virtual interface with a counterpart interface in the host system. So it's basically like a network cable with two links, one in the namespace of the container, the other one in the host system. And in the host system, there's usually a bridge or a couple of them, and those containers are connected to those bridges and then can talk to the other containers connected to that bridge, and there usually is a net gateway to the outside, so those containers can, for example, download data or connect to the outside. When creating user-defined networks, Docker usually also provides DNS. So it's possible to start a container and say, okay, I want this container to listen to the name DB. And then Docker provides a DNS server resolving queries to this name DB to the IP address of that specific server. So all you're saying is, I have this server, this container, I want to call it DB, and then another container connected to the same network is able to just connect to DB, and then it ends up on this specific container. And that brings you a lot of flexibility when you think about decoupling different tasks into different containers. So for the internal communication, that's pretty easy. We have this bridge, we have one subnet assigned to it, the containers get IP addresses in that subnet, they can resolve their names, they can resolve their aliases, they can talk to each other. However, those networks are specific to the one Docker node or to the one Docker Swarm cluster that you're running. So they are not connected to the outside. And you also can't really predict the IP addresses of the containers. If, for example, you have an update and you just recreate your containers, they might get other IP addresses than they used to have before. So when you want to connect to those containers from the outside, you need an additional component. And at least when you're doing classic Docker, you're doing some kind of destination nut, meaning that the host systems, which usually have fixed IP addresses that are well known to the outside, open a port and redirect all traffic that's going to this one port to a certain set of containers offering a specific service. So for internal communication, you have one subnet per network where the containers can just talk to each other. For everything that you want to have exposed to the outside, you need to have those port forwardings, which are easy to do with Docker. You're just saying, okay, I want the external port 80 to be forwarded to port 80 of a certain set of containers. But it's still, some kind of decoupling, and you only can use each port of the host systems once. So if you want to have a second web application on the same Docker cluster, then you need a different port, for example, port 81 or something like that. Let me try to summarize this. Then we have those containers, each container running one task, and for an application that's built of multiple components like web server, database server, logging server, memory cache, whatever, we need a couple of those containers, which need to be all set up in a certain order, which need to be connected to the right networks, which need to be configured with the right aliases and names, which need to be connected to the right volumes. Setting all this up manually is pretty painful, especially if you want to do it again and again and again. And then you want to do it a second time to have it as a test system, for example. And that's where container orchestration comes in. Container orchestration basically tries to do exactly those things. When you have an application, and usually we're talking about microservice applications here, running on multiple services with multiple supporting other services, then we need someone who's able to start those containers, to connect them to each other, and some entity who's also able to manage deployments. Saying, for example, okay, I have 20 web servers running on an old version, now I fixed an error and I have a new image with the updated version of my application, and I want to roll that out. But maybe I don't want to replace all those 20 instances I have running. Maybe I just want to replace one and see how it's going. Right? I keep 19 of the old ones, I shut down one of the containers, deploy a new one, and then I see if this container spins up and if it's working well. And if it does, then I do it with a second container. So I have 2 containers with the newer versions and another container with, or another 18 container with the old versions. And then time by time, I'm replacing one container after the other until I'm on my new release. And container orchestration is providing all the abilities to do that. When we talk about container orchestrations, we usually have 2 tools that are commonly talked about. One of them is Docker Swarm and Docker Compose. That's like the smallest solution. And we have the big flagship that's called Kubernetes. That's what everybody's talking about these days. There are a couple of other ones, but those are the ones that when you start to do some research related to this, you usually end up with. Docker Swarm and Docker Compose are pretty tied to what we've already seen. So you're talking about individual containers. You're describing, like, I want to set up this container and that container. I want to set those environment variables. I want to connect them to this and that volumes, to those networks. Whereas Kubernetes has some more structure around this. And the smallest entity that Kubernetes uses to manage containers is a pod. So when you work with Kubernetes, you're not working with individual containers, you're always working with pods. And the easiest way, a pod is only like something that contains one container. But it can contain more than one container. The nice thing about a pod is all containers belonging to one pod always end up on the same node in your cluster. Like usually you have a big cluster with a lot of Kubernetes nodes. But when we think about, for example, a log processor for an application, then you want to have the log processor running next to your application. You don't want them to end up on different nodes where in the worst case they even can't see the data. So you want them to always exist at the same place. So putting them into a pod makes sure they are always scheduled next to each other on the same node. Also, a pod shares a networking namespace, meaning that those containers can talk to each other on localhost. So if you have, for example, a web server running on port 18 and you have a second application that's, I don't know, sending a request to trigger some action in your application every 5 minutes, then they can just do this on localhost. So you don't have the need to set up some names and some networks in between these things. If you try to put it in a graphic, a pod would, like, again, super simplified, look like this. We would have our pod with 2 containers, each isolated in a certain extent, but sharing one networking namespace. Again, we have Docker containers in there with the regular images with those specific thin layers in there, but the pod is the entity that Kubernetes uses to manage those 2 containers. When we want to have volumes attached to that, Kubernetes offers us 2 additional resources. One of them is something called a persistent volume. That's a place to store data. And there's a so-called persistent volume claim. So Kubernetes tries to decouple the places to store data from the request of being able to access it. So if you have a pod, this pod can have a so-called persistent volume claim, which is basically the question to Docker saying, okay, we need a volume with 5 GB of size, and then Kubernetes is trying to either assign a volume, or if you have so-called storage classes, to create a volume. And that's something that's really handy. If you're in the cloud, for example, it's possible to have a persistent volume claim, and Kubernetes creates a volume in the cloud for this one claim. It's also possible to integrate it, for example, with your VMware infrastructure. saying, okay, I have a VMware data store, and when a container needs a volume with a persistent volume claim, then there's a volume created in this data store. So that's a pretty high level of integration and of letting Kubernetes taking care of preparing all these environments. Likewise, there's something called config map or secret, however you want to call it, and that's a way to store basically key values, like a configuration, for example, saying that's a username to connect to my database, that's a password for this user, and then make this information available on the container either as an environment variable or as a file. So it's possible to say I have different config maps, one for my productive installation, one for my testing installation, then run the very same pods just with the assignment of different config maps and different secrets. And those persistent volumes, as well as the config maps and secret, are not specific to a pod. So they exist in the Kubernetes configuration, and they can then be assigned to one pod, to multiple pods, and they can even live longer than a single pod does. So if I, for example, have my configuration in my config map, it's easy to replace a pod by a newer version, but keeping the same config map with the same configuration data. The biggest challenge when trying to somehow create Dockerized or like Kubernetes-specific applications is handling those pods. Like it's easy to define a pod, but usually you want more than one, especially if you have microservices. And Kubernetes offers two more objects. One of them is the so-called replica set. That makes sure of running a certain pod several times. Saying, for example, hey, I want 20 web servers. Then you can have a replica set ensuring that you have those 20 copies. And the replica set takes care of starting additional pods if you need more, or deleting pods if for some reason more of those pods show up. And there is a deployment that's, again, like a higher level. That's an object creating replica sets. And that's useful when you want, for example, to do a deployment. If you say, I have a newer version of this, then you can have two replica sets, one for the older version, one for the newer one, and then scale one of them down and scale the other one up to somehow shift your traffic from the older to the newer version. So if you try to put it again into a picture, we still have our pods, and we usually have a couple of copies of the same pod. We have the replica set managing those copies, and we have the deployment creating those replica sets. And as you're seeing here, that's a huge amount of terminology and a huge amount of concepts and configuration resources. And we still have no volumes in here, like no persistent volume claims. We are not showing config maps in here. We're not talking about network policy objects. So these configurations can become pretty complex. But it's a great way to abstract the deployment of those individual containers with all their details, so that in the end, you end up with a deployment saying, I want this version of my image being deployed 20 times for my production environment with this and that config data, and then Kubernetes takes care of setting up everything else. The only thing missing in here is the ability to connect to those containers. Like, it's fine to have 20 web server containers running, but it's still necessary to make them somehow reachable from the outside. And that's where services come in handy. Services basically select a couple of pods. Every pod has a series of labels. Those labels are like sticky notes that you put on it saying, that's my app, that's my version, that's, I don't know, color green. And then you have a selector in your service saying, okay, incoming requests to the service should be distributed to all containers that have the label application 1, that have the label deployment green, for example. And you can move those labels between your containers and between your pods, sorry, and you can add them to your pods and remove them from your pods, and the service immediately adjusts by balancing the incoming requests to those pods. These services are, again, usually running within your Kubernetes cluster. So if you want to expose them to the outside, you either need a cloud provider doing that for you, you need to assign them to ports of your host systems, or you can have a so-called ingress. An ingress is something like a reverse proxy that sits in front of your services, takes requests from the outside, and an ingress, for example, is able to have name-based virtual hosts, saying if I get an HTTP request with host name A, then I assign this request to service A, and service A then has a selector that says which pods are relevant for this one request. And at the same time, it's possible to say if I get a request with host header B, then I assign it to service B, that then has a selector picking all the nodes that are able to serve this one purpose. So we see that Kubernetes has a lot of different resources, and all of these resources somehow need to be managed. Usually you're doing this in YAML files, but you'll sooner or later end up having a couple of them, and you'll sooner or later be at a point where you want to somehow modify them. To say, for example, that's version A, that's version B, that's productive, that's development. And that's where a tool called Helm comes in handy. Helm has so-called shards, and a shard is basically a set of templates for Kubernetes resources, but Helm provides modifying them whenever you deploy them. So say, for example, I have a variable here, and Helm takes care of putting this variable into all the different Kubernetes resources and applying them to your cluster. Helm is one of the younger tools that's pretty prominent these days, especially because there's a library with a lot of existing so-called shards. So you don't have to take care to, for example, write your own Helm shards if you want to have a certain database service, because there's a high chance that someone else did that. And you're able to just say, OK, I want to download this one shard and deploy it, and then you have your application running, and you're probably good doing this. Of course, you can have own Helm shards for your own applications in your own internal repository. When you try to set up an application like that, you end up with a pretty big zoo of containers, of pods, and you're not really aware of the individual behavior of those pods because you're not the one managing them. If, for example, you say I have an update, then it's up to Kubernetes to decide which pods it kills and recreates and when it does that. So the application running within this pod could be terminated at any point of time because there's a newer version, or because a host system is going down and the container is just terminated here and restarted somewhere else. And as it's really terminated and deleted, this thin layer with all the status information, for example, is lost. So our application needs to be aware of these circumstances and needs to be able to somehow recover if something like that happens. So as our application container run one service at a time, first of all, we don't have any init system, so we can't, or at least we shouldn't have any supporting services running there. So when we design such an application, we must create containers that all serve one purpose, running one application. That's, first of all, pretty easy, but when you have a couple of those services, yet the individual amount of having different containers can be pretty huge. Then you certainly want some kind of orchestration tool because you don't want to create all those containers manually, but you want a tool to manage that for you. The design of these tools are a little different depending on which ones you're doing, especially if you compare Docker Swarm to Kubernetes. You have a lot of differences in the networking area, but you should definitely pick one of those tools and try to create the deployment of your application using the means of an orchestration system. Your application itself is wrapped in those images, and your orchestration just tells your cluster which of those images you want to run and how often you want to run them and in what environment. The images serve as some kind of tool or some kind of format in order to move your applications to the production server. So instead of having, for example, a tar archive that you're unpacking into a specific distribution and you hope that all the libraries fit and that everything is installed, you have everything you need to run this application within this one image. You create them with Docker files, as we've seen, and it's actually worth to take a look on Docker Hub and see what's up there, because you'll find, for example, for Redis or MariaDB, you'll find prepared images that you could just use. But you should be careful who created those images, because basically it's possible for all of you to just create an account and upload images there. You see that by a username included in the image name. So, for example, if there's Fabian/whatever, then you know it was a user called Fabian that created it. And that's not me in that case. But you don't know what those persons did with those images. And there was a research done where someone found a couple of images named similar to image names used in some tutorials, just with a few typos, containing some crypto miners, for example. So don't just run anything that's up on Docker Hub, but see who created it and maybe take a look into it, what it's really doing when you start. When you create your own images, try to avoid any configuration time when the container starts. Try to prepare everything that you can prepare in advance at the building time, when you take your Docker file and you turn it into an image. and at the same time try to decouple all configuration from the content of the image by reading environment variables, by reading the files created from, for example, Kubernetes secrets or config maps, by using some implications in the sense of connecting to specific host names, and then have your orchestration setting up those host names with the correct services. In that case, you end up with images that you can reuse in all your environments that ensure that the software runs the very same in production as they run on the testing system, and that don't require any configuration when you start them, so you can immediately run your services in your containers. Your application should be aware of some of those requirements, and the hardest requirement is persistency. So whenever your application stores something that you want to review later or want to keep for some reason, then it should do so in a very specific path. So you can have a volume on those paths and make sure that all the data written by your application ends up on this volume and nowhere else. Because if it's stored at a place in the container that's not attached to a volume, it will be lost. That's the most important aspect. Know where your application stores data and make sure that there's a volume. Or avoid storing anything in the file system by, for example, using an object store and putting all data there, or use Redis or an SQL database or some kind of external tool where you're putting all this information. Also make sure that your application can be terminated at any time, because when it's time for an update, the application will just be stopped and restarted with a new version. And not all applications really behave well if you just terminate them and start them another time. Or if you want to scale them up. If you say, for example, hey, one server is fine, but I want 20 of them now, and your orchestration software just starts the same container 20 more times and connect this one instance to the same volume 20 more times. That might lead to data corruption if the application is not designed to be run like that. So make sure when you think about putting applications into containers that the applications are fine with those circumstances. And that's not necessarily the case for all applications. There might be applications that have a lot of different requirements. So that's more or less a summary of what we've already talked about. Think about how you want to distribute the components of your application into containers. Think about, for example, those sidecar containers, saying I have my one main server doing something, and then I have a series of surrounding containers. One of them might, for example, download additional files, like if, for example, you want to have rates from a stock exchange in your application, you could have one application processing this data and a second one downloading it every 5 minutes or so. Or if you want to ship log data, that could be one of those sidecar containers as well. And think about logging and monitoring. And think about how they scale, in the sense of you not have one instance of your application, but you have a lot of those instances. And they all log, and they all need to be monitored. Security is another important aspect, and unfortunately, a lot of people think about, or mostly think about, how secure are containers in themselves. But usually, the incident that happens is not that someone breaks out of the container, but usually the incident is that someone just gets an image from somewhere, runs it without thinking about how can I secure this application, and thereby exposing the data in the application to the outside. So make sure that you understand how to harden your application. Avoid applications that run with root privileges in your containers. Think about limiting what your containers can do, in the sense of not letting your sidecar containers consume all your resources, but leave them for the main application. And whenever you download images from a public place, make sure you take a look who created those images and do you consider those images trustworthy. Because whatever is in there is run in a container, but it's still run on your hardware, on your IP addresses, on your computing resources. So a final word in this area about virtualization and containers. That brings us a little back to the beginning of the talk. Containers, at least application containers, are no real replacement for virtual machines. But instead, they are something that go hand in hand. In almost all cases where I've worked with those clusters have been deployed in virtual machines. That, in the most cases, allowed us to have something like cluster as a service, saying, hey, I need another cluster to test something, or I want to have a dedicated testing cluster for for something to do with my application, to just spin off a couple of VMs, redeploy the cluster, and have the same or similar cluster running again. Likewise, it enables you to somehow segment what you're doing. So, for example, to avoid your developers from being able to overload a cluster that is somehow running a productive instance of your application. And if you integrate this containerization with your virtualization, you might get a couple of benefits, especially if you're running in the cloud. So that you could, for example, have a service, and the cloud provider takes care of configuring a load balancer for your service. Or that you have a persistent volume claim, and there's a volume created in your virtualization to fulfill this claim. That's a lot of configuration effort, but it's great to implement it, and that brings you a lot of flexibility in there. So when we try to summarize this, then we know that those application containers are different to traditional VMs, and they are also different to those these VPS servers that you might have known from being sold for a few dollars at your favorite internet provider. You know that they can be created, restarted, killed, scaled at any time, and that your application should be aware of that. You know that they rely on an image, that there are images that exist in the outside, and that you can use those images in order to add your specific application, your specific tools to it, to then have an image that you can just run in your own production. And the administration of those containers is, again, different to what you know from traditional virtual machines. So you're not logging in there with SSH and trying to explore what's going on. You might save the container for later investigation, but you just start a new one and hope that one runs better. For the applications, it means that your application must somehow be able to survive in this environment. It must survive being restarted. It must survive being scaled. It should store data only in very specific places that you have provisioned with, for example, volumes. If you want to get some more details about how these applications can be designed, there are a couple of resources that I'd like to share with you. Some of you probably heard about this 12-factor app manifest. That's a collection of 12 things, 12 requirements that cloud-native applications, like applications living in such an environment, should do. That's really worth reading, and it contains a lot of good hints when you design applications, how to design those applications that they can run in such an environment. There is a paper from 2 Google engineers describing some architectural patterns. One of them are those sidecar containers that we talked about, but they have a couple of more. If you start to learn Kubernetes, it's important, besides having some general introduction thing, to stay up to date, because there's a lot happening, and really every week there's a lot happening. Google has a really nice podcast explaining what's happening. They have a news section every week, and they're covering different topics. And from my perspective, it's one of the best resources to stay up to date with what's happening related to Kubernetes. And finally, if you're interested in some more general ideas about DevOps tools, what's related to it, and you want to get an introduction to that, go to the LPI blog. We have a blog series that covers some of important DevOps tools. Some of them are containers. And that's the only advertisement I have in here. And I think we have 3 minutes for questions. So if someone of you would like to ask something, we have a special microphone for you.
Question.
Wait a second. Oh. So you're getting a microphone.
How do you manage a live update of the database and containers?
Database updates are actually something that are really complicated, especially if you have schema updates. Because then you'll end up with 2 versions of your application expecting different schemas in your database. And what we are trying to do, and so far we were successful in doing that, we try to somehow stay backward compatible. Trying to not move data away from where the old version expected it, but just add stuff. But that's a privilege of developing an application from the ground. It's not common that you're able to do it like this. If you're doing it that way, then it might be desirable to have some kind of API in between. Saying that you have an API that's used by all the other services or containers to interact with your database, but then you can have some compatibility in your API, saying I have version 1 of my API, and I somehow adjust that to be able to work with a new scheme. Then you can update the database scheme, and this proxy in front of it, but that decouples all your different applications from being modified at the same time, because you only need to modify this one proxy in front of it. But it really depends on the size of your database and how often you're changing that, and if you're backwards compatible or not.
And so you do one of the ways container and the second container with the new schema and just copy the data?
No, I wouldn't necessarily copy it. I would have my database in one place and only in one place. It might be possible, for example, to have a set of containers in front of it, and those containers are the only one directly interacting with the database, and they provide an API to the outside. And all other services use this API instead of directly connecting to the database. And then it's possible to update the database and only those services in front of it. But as long as the API to the outside stays the same, all the surrounding services don't have to immediately be updated. And if you versionize your API, it's possible to keep the old version running for all the surrounding applications, and have a newer version of the API that then leverages those updates in the database scheme by new services, which then can be, again, updated the traditional way by rolling updates and something like that. But you want to decouple this if that happens every once in a while.
Okay, thank you.
Anyone else? Can you pass the microphone back?
Hi, you spoke about using trustworthy images.
Yes.
How do you propose determining whether it's trustworthy? so far in our continuous integration, we use GitLab CI. So far, I've just read all the Docker files, but that doesn't seem to be a useful solution because it takes a lot of time.
It depends on what's the thread that you're seeing. So when you're getting images from an external source, like from Docker Hub, the most important aspect is to check if there's a slash in the name. If it's like username/image, then you know it's not like an official image, and then you should definitely give it like a closer look. If there's no slash in there, for example, like CentOS or Debian or Redis, then you know it's an official image, whatever official means in that case. But on the other hand, if you're downloading, for example, a Debian installer from debian.org, then you're somehow trusting that too, right? So the question is always, who do you trust and who do you not trust? And the alternative would be to get an empty container, compile everything on your own after reading the source code, of course. I mean, you all do this. And compile it on your own, put it into your container, and hope that you haven't overseen anything there. And then do it like the same for the next update. So that's a big question on what's your trust anchor in there. If it's for your own containers internally, it's definitely a good idea to secure your registry, so you're sure that no one within your organization can tamper with it. But that's like another kind of attack if you expect someone to mess around with your own internal registry. And what's super important when you think about pushing images to GitHub, to Docker Hub, think about what's in there, right? Don't leave any like S3 access keys in there when you push it to a public. Yeah, it really happens. When you push it to a public registry.
Okay, thanks.
So I think we're already a little over time. If you want to keep talking, I'm at the LPI booth today. If you want to talk with me about software licenses, come back to this room at 2 o'clock. And otherwise, thanks for attending and good luck with Docker, Kubernetes, and all your containers.